so we're given this set transfer from a given filter, and we want to find the pole zero graph and the filter response, and what type of filter this set transform represents. So first of all, we're going to multiply everything by set to the 4 in order to get positive exponentials, and we get this. Then we want to find the zeros. So the first zeros we're going to find from this equation. So we get set to the 4 plus 1 is equal to 0. We get 0 to the 4 equals minus 1. And then we get 2 zeros. Well, 4. So we get plus minus 1 to the 4 to the a quarter. And then we get z equals plus minus 1 to the 3 over 4. And then we get, from these, we can get these two. So we get e to the plus minus j pi over 4 and e to the plus minus j 3 pi over 4. So then we can place these 4 zeros on the graph. So we get from here, we know that the angle is pi over 4, plus minus pi over 4, so we get this 0 here and this one here. And from here we know that the angle is 3 pi over 4 and minus 3 pi over 4. So we get this 0 here and this 0 here. Then from the denominator, we can find the poles. So for the first equation here, we can get z equals to 1/3 and minus a half. So we put them here and here. And we get from the second equation, from this equation here, we get z equals plus minus j 1 over 5, which are these two poles here. Then for the filter response, we have to de-emphasize the frequencies when we get to zeros, and we have to emphasize them when we have poles. So we have pi over 4, minus pi over 4, 3 pi over 4, and minus 3 pi over 4. So we know that those frequencies need to be de-emphasized. So we have here we get to 0, and here too we get to 0. And then for the poles, we have to emphasize the frequencies, and that's why we have these little bumps here. And from the filter response, we know that this filter that we're giving is a bandpass filter with 3 bandpasses.
So now for the finite differential equation, we know that h of z is equal to y of z over x of z is equal to this thing. So now if we cross multiply, we have the denominator is equal to y of z and the numerator is equal to x of z. So if we multiply each term, we get this thing, and this for times x of z. So by rearranging the terms and adding the similar terms from these two, and that's pretty much it. So adding them gives this, times y of z is equal to 1 plus z to the minus 4 x of z. So now we're putting in form of y to the n. So we have exponent minus 4, so it's already in the negative form. So we just go from there to there. So y of n minus, so it's minus 1 over 150 y of n minus 4 plus 1 over 150 y of n minus 3 times minus 19 over 150 y n to the minus 2 plus 1 over 6 y of n to the minus 1 plus y of n is equal to x of n plus x of n minus 4 plus x of n minus 4. So in order to be stable, the ROC needs to be the outside of the leftmost pole. So if we make a circle around the pole at negative 1/2, the leftmost pole, the ROC has to include the unit circles, so that's why the ROC is greater than 0.5.
So for this problem, we want to find the output of the filter to this input without doing any complicated computations. So as a result, we're going to make some assumptions. So basically, for the pass band, we'll just assume that it perfectly passes our signal, and for the stop band at these frequencies, it'll perfectly attenuate the signal. So here we have this input. Each of these terms has a corresponding frequency, and based off of this frequency, we'll determine whether or not that passes or is filtered. So we look at -1 to the n. This is basically just a signal with the angular frequency pi. So we look here at our plot. That is in the passband, so that is going to make it to the output. We look at 2 cosine squared pi over 4n, just using the trig identity. Yeah. So when we're looking at our input, we want to see which signals are going to pass based off of their frequency. So we look at -1 to the n. This signal has a frequency of pi because this is going to be alternating between -1 and 1. So we look at the frequency pi, that's in the passband, so that's going to make it to the output. We've got 2 cosine squared pi over 4. We can apply this simple trig identity here for cosine squared, and this is the result. We can see we have a DC term here, it's going to be +1. There's this is a DC component, there's no frequency, so the frequency is 0. That is associated with the passband, so that's going to make it to the output. As for cosine pi over 2, once again, the frequency is pi over 2 in the passband, so we'll make it to our output. Here, look at it again, sine squared, pi over 8n. Applying a similar trig identity, we obtain, we obtain 2 signals, 1 minus cosine pi over 4. So the frequency is 0 and pi over 4 are both in the passband, so they make it to the output. As for this last signal, this one has a frequency pi over 4. We can see pi over 4 is one of the signals that's attenuated, so that will not make it to the output. As for this last term, sine squared, pi over 5n plus pi over 3, we plug this into Wolfram alpha and obtain the result here. So we can once again see a DC term and then a term with a frequency of 2 pi over 5. That is also in the passband, so that will make it. So as a result, this is our output, assuming that the filter is ideal.